In today's video lesson, we're going to look at acid-base equilibrium problems using the icebox method, and we're going to focus more on a weak acid equilibrium. After we do our summary lesson, we will cover one of the older AP Chemistry exam questions as a sample problem. So I thought it would be a good idea to first do some review and look at an equilibrium equation here with a weak acid that I've just called HA. And so I'm going to label this as my weak acid, or WA, weak acid. And I know it's a weak acid because it's undergoing equilibrium. So if I look at the double arrows, that represents that it does not dissociate fully into products. Now, how do I know it's an acid? We have to remember the Bronsted-Lowry equation of acids. So Bronsted-Lowry acids are those that donate H ions. So if I look at HA as a reactant, as a product, it became A minus. So that means that the HA donated away a proton, which is this H plus ion. It donated it actually to the water, okay? Now, if I look at the product A minus on the other side, we call this one our conjugate base. It's a conjugate base because the definition of a Bronsted-Lowry base is that it'll be an H plus acceptor, which is what the negative ion is able to do if we actually go backwards in the equation. Okay, now the water and the hydronium in this Bronsted-Lowry equation, the water is acting here like a Bronsted-Lowry base as it is a H plus acceptor, because if I look at it from here as a reactant to a product, we can see that it accepted H plus to become hydronium, which is my conjugate acid in this kind of relationship, okay? Now that I have this kind of acid equilibrium expression or this equation in my mind, I can actually record the acid ionization or the acid dissociation constant, Ka, or also just known as the equilibrium constant for acids. So the equilibrium constant for this, by the way, if I was to do a sample question, we could have a little icebox situation where the ice, the I is the initial concentration of my reactants and products. You remember that products always start at 0, and then the change is my products will always increase by X, and by their mole ratio. This is a 1-to-1 mole ratio, and at equilibrium, so my products will be X. The water we don't consider because there's no concentration of water. We're only looking at the aqueous components. And the weak acid, when we do a weak acid equilibrium, we can use something called approximation, where it should be minus X on the left side, on the reactant side. But because the weak acid barely dissociates, we can assume that whatever the initial concentration was, it will have a very similar concentration at equilibrium. So this is kind of a setup that we can use in these kinds of problems, and we want to specifically focus on this part, the equilibrium concentrations of the reactants and products, because I will use this to determine Ka, which is always going to be the concentration of your products, so in this case hydronium and the conjugate base A minus, over the concentration of the reactants, which in this case is HA. Okay, now additionally, before we look at our sample question, where you see hydronium, I want to remind you there are some useful formulas to help us determine this X value. So there's a formula where it's pH equals negative log of hydronium. And if you actually take the anti-log, so I can use this formula to calculate the pH if I knew how much hydronium there was, or if I'm given a pH, I can use the pH to calculate how much hydronium I have. So the concentration of hydronium is 10 to the power of negative pH, or the anti-log. So those equations will help me, and same with my equilibrium expression as we look at a weak acid problem. So let's move on to a sample question here and see how we feel about this one. So we're given a propanoic acid, which the formula is shown, and it's a carboxylic acid that is reacting according to the equation. And I have a certain concentration of it and a certain pH of it. So I first want to identify the Bronsted-Lowry conjugate acid-base pair relationship in this equation and label which one is the acid and base. So do you remember from our sample lesson up here, I said that the Bronsted-Lowry acid is an H plus donor. So what you have to do is you have to look at these two compounds and figure out which one gave away H. So if I look at the products of the equation, the products of this reaction, what I can see is that this compound here, this propanoic acid, it loses this H ion to become CH3CH2COO minus. So my Bronsted-Lowry acid is propanoic acid, and it's labeled for me as well, right? So that's actually a hint as well, but I know that because it's giving away the H+. Now it says here we should identify the pairs. So if that's my acid, remember this this is going to be this negative ion that it produces. That's going to be my conjugate base. So the conjugate, now you could probably label it on the equation, but I'll just write it down underneath. The conjugate base is CH3CH2COO minus. Okay, and you could also label the water as your Bronsted-Lowry base, and the hydronium is your conjugate acid. So let's solve this question. Determine the value of Ka for the propanoic acid at 25 degrees Celsius. So the temperature is constant. Okay, so I'm going to rewrite the chemical equation here for part B. And what I'm going to do is I'm going to set up an icebox. Because in order to calculate Ka, if you remember what I was doing before, I'm going to need to know the concentration of reactants and products at equilibrium. So initially, so let's set up our ice chart. Initially, so again, sorry, the water we don't need to worry about. Initially, I have a 0.2 moles per liter sample of the acid. And remember that the acid will change by minus X. This is again a 1:1 to 1:1 mole ratio. We just moved a hydrogen ion, so there is no coefficient. So at equilibrium, I'm going to use the approximation method here. And I'm going to say that I'm doing that, okay? So if you're answering this on an exam, you should absolutely say that you're approximating. So I'm going to do that because it's a weak acid, and I can tell again by this equilibrium arrow. You can also, if you don't want to approximate, you could just do the entire mathematical solution, but just to save time, I'll approximate. Moving to the product side, both products here start at 0 moles per liter, but they will increase by X. So at equilibrium, they will have a value of X. Now, I have some information that will help me figure out my X value, and that's this pH. So do you remember how I showed you guys up here that if I'm given the pH, I can convert that to hydronium using this using the anti-log formula. So let's do a little work on the side here. We're going to say that the H3O concentration is 10 to the power of negative pH, which is negative 2.79. And so that will give me a hydronium concentration of 1.6 times 10 to the power of minus 3 m. Okay, so what I could actually do is plug that value here, right? And that actually becomes my X value as well. So because it's 0 plus X equals hydronium, and that will therefore also become the value of my conjugate base as well. So now that I know the equilibrium concentrations of all of my reactants and products, remember water doesn't count, I can substitute them into my Ka formula, which is Ka equals, so I'm going to try to squeeze this here, Ka equals concentration of products, so my conjugate base, times hydronium, divided by the concentration of the acid. Okay, so we're going to plug all of our values in. Again, these are going to be raised to the power of 1 because we do have to raise them to their mole ratio. So this becomes 1.6 times 10 to the negative 3 m. It's squared, okay, because it times itself, divided by the concentration of the acid, which remember I approximated is 0.2 moles per liter at equilibrium because it's a weak acid, so it did not change by very much. And my final answer for Ka rounded to 2 significant digits here to reflect what we're given in the question, 1.3 times 10 to the negative 5. And that makes a lot of sense. Okay, for a weak acid, we definitely expect the K value to be less than 1 because that means that we favor the reactants. Okay, so we'll pause it there, and if you're interested in another topic and another sample problem, I'll post the next video shortly. Thank you so much for watching, and you can leave any questions you have in the comments. Thanks.